Alright, so welcome to the second tutorial on beam problems. In this second example, we have cantilever beam, it's fixed at one end, and we have a distributed load acting on the beam. So the first thing that we're going to do is we're going to find our reactions, and the second is to find the shear and bending moment values. This beam is 8 meters long, beam is 8 meters, so we're going to find it halfway through the beam. First thing that we need to do is find the reactions. So cantilever beam, we have 3 reactions. We have the Y, the X, and we have a moment. Let's say this is point A, and let's go and write our equilibrium equation. So we have sum of forces in the X. So any forces that are acting forwards or backwards. And we'll say backwards will be negative. Any forces going forwards will be positive, right? So here, if we look at our beam, we don't have any forces acting in these directions, right? We have no forces. We just have our reaction, but our reaction occurs because of the forces acting on the beam. So we have no forces and no reaction. So we can say AX is equal to 0. Next, we have sum of forces in the Y direction. So forces acting up or down. We have, let's say, forces acting up will be positive, forces acting down, negative. So we have our reaction acting on the beam. We've drawn it as a positive, so we can go positive AY. And then we have our distributed load acting in a negative direction. We need to convert this into kilonewtons, right? Into kilonewtons. So how we do that is we multiply it by the distance and we'll end up with the kilonewtons that we need. These values are in kilonewtons, right? So we'll have a negative 10 kilonewtons per meter times 5 meters. And this will be equal to 0. So if we simplify that, our AY will be equal to 50 kilonewtons. And then we have sum of moments about point A, and we have moments acting in the anti-clockwise direction, we'll say positive, and moments acting anti-clockwise, we say are negative, right? So we'll have, if we go to our beam, we'll have our positive reaction, right, acting in this direction. So we have plus moment A, and then we have our negative moment caused from this distributed load acting in this direction. So our moment will occur halfway between this distributed load, right? So we can imagine we have like a point load acting here. Okay, so we have minus 10 kilonewtons per meter multiplied by 5 meters. We get our point load, and then we need to have this distance, right? It's going to be acting along this distance. This is the distance of our moment. So we have multiplied by, so this distance will be 2 plus this distance here, right? So this distance will be half of 5, so 2.5 meters. So we'll have a total distance of 2 plus 2.5, and then this will be equal to 0. So if we solve this, we'll have MA will be equal to 225 kilonewton meters. All right, so now we have our reactions, right? So we've solved our reactions, and now we can find our shear and moments. So what we can do is we can draw our diagrams. Let's redraw our beam with all our reactions. So our MA was 225, our AY was 50, and our AX was 0. And then our distances, so it's 5 meters, we have 2 meters here, and this was 1 meter. Okay, so now we have our beam, and we can draw our shear and moment diagrams. Shear force diagram and bending moment diagram. And this will be a positive, negative, and this will be positive and negative side. So let's have a look at our shear. So we have our 50 kilonewtons going up in the positive direction. We're going to move across till we reach the 2 meter point. We have the distributed load of 10 kilonewtons per meter acting down, right? So this will decrease linearly 10 kilonewtons per meter, and we have 5 meters. This will decrease to 0. So this will decrease linearly here, and then we finish off at 0. And then our bending moment diagram, we're going to have a negative 225 acting down, and then we're going to have an increase. So we'll have like a linear increase at our 2 meter point, and then it's going to curve. It'll curve until it reaches the 0 point, and then we have 0. So the question was to find the shear and moment at 4 meters. All right, so let's have a look. Let's have a look at 4 meters. So 4 meters is halfway. So let's say that's 4 meters. So this distance is 4 meters. And what we can see is we have a curved line for our moment. and we have a straight line for our shear. So our shear won't be too difficult. We can use similar triangles, or we can develop our function. With our moment, because we have a curved line, we don't know what this value is going to be. So we need to find our moment function. So let's do our shear first. So if you see our triangle, we have a triangle that's like this, and we have a cut section. So we want to find this value here. We want to find this value here. And we know this value is 50 kilonewtons. And we know this value, which is 0 kilonewtons. Okay, and we know our distance as well. We know our distance. So we can say this is 0, and we can say this is 5 meters, right? And we want to find our point at 4 meters from the beginning of the beam. So this is going to be, we can say this distance is 2 meters. All right, so what we want to do is we want to find this point, and the value at this point. So what we can do is we can write 50 kilonewtons minus 0 kilonewtons divided by 0 meters minus 5 meters. And this will be equal to, say this is x. We want to find our x value, right? So we can go x minus 0, and we know that this point is 2 meters, right? So we can write 2 meters minus 5 meters, right? And we solve for x, we can find our value. So our x value, if we solve for x, our x will be 30 kilonewtons. So that's one way we can find our shear value. So we found our x value at this point, 30 kilonewtons, using similar triangles, or we can develop our shear function. All right, so let's find our shear function and our moment function. So what we can do is we can cut the beam along this section, and we can analyze just this section, and we can develop our moment and shear functions. All right, so let's redraw our beam. So we have our cantilever beam, and we've cut the beam at a certain point. We have our distributed load acting down, 10 kilonewtons per meter. We have our reactions, 225 kilonewton meters, and we have 50 kilonewtons up. So this distance is 2 meters, and this distance, we'll consider it, we'll say it's x1, right? So we'll say that's a distance of x1, and we're going to draw our shear. We're going to have a shear value, and we'll call that V1, and we have our moment value acting around this point, right, in a positive direction, and we'll call that M1. Now we can develop our shear and moment functions, our V as a function of x1. All right, so just keep in mind that you can write shear or this moment in the positive or negative direction. It's up to you what you want to do. But I'll write my V1 in the negative. Okay, so we have a negative V1, and then what other forces are acting on this beam? So we have a positive 50 kilonewtons. So we have plus 50 kilonewtons. We have a minus 10 kilonewtons per meter acting at a distance of x1, right? Minus 10 kilonewton per meter multiplied by x1 meters. And this will be equal to 0. So we'll have V1 is equal to 50 kilonewtons minus 10x1 kilonewton. Okay, so now we found our shear function. Now we can find our moment function. So we can write our moment as a function of x1. So we can write that, right? So we have our positive moment acting around this point, around our cut section point. So we can write positive m1. Now we have a negative moment of this 50 kilonewtons acting in the anti-clockwise direction. So we can write negative 50 kilonewtons, and the distance is 2 plus x1. The distance is 2 plus x1. We also have a positive 225 kilonewton meters working in this direction. So it'll be a positive 225 kilonewton meters. And finally, we have our 10 kilonewton per meters acting in this direction. All right, so we need to remember, we need to convert this into a point load, into kilonewtons, and because we're dealing with moments, we need to multiply it by distance, right? By meters again. So we need kilonewtons, meters. The distance that we're working with is x1. All right, so it'll be plus 10 kilonewton per meter, and then we'll have multiplied by x1. So this will be kilonewtons. This will be kilonewtons. This will be the point load, and then we need to multiply it by this distance, right? This distance to make it a moment, right? It's going to be acting around this direction. So we have multiplied by x1. The distance is x1, over 2, right? It's halfway of x1, so x1 over 2. And then this is finally, this is kilonewton meters, right? This is kilonewton meters. This is what we want. All right, so if we solve for m1, m1 will be equal to negative 5x squared plus 50x minus 125. Now we can plug in our numbers, right? So the distance we're looking at is, if we look at our beam, is this distance, right? Which is 2 meters. Because this distance at the beginning is 2, and then we have 2 plus 2. This will be 4 meters along the beam, but we're only looking at this distance. So if we plug in 2 meters into our equations, we can find our shear and moments, right? So let's do our shear first. So our shear, 2 meters here. Let's write our shear equation. So we've got 50 minus 10 times 2, which will be 30 kilonewtons, right? So it's the same value that we found using the similar triangles. So let's find our moment. Our moment is m, the function of 2 meters. So our m will be negative 5 times 2 squared plus 50 times 2 minus 125, which will be equal to negative 45 kilonewton meters. So now we found our moment and we found our shear values at 4 meters. So if we come back to our beam, this value here will be negative 45 kilonewton meters. So that's the solution. We have a negative 45 and we have 30 kilonewtons at 4 meters.